like the ear. It's now being seated with cartilage. That's the mold. That's the oven-like device. Once it's coated, it gets placed there, and then a few weeks later we can take out the cartilage scaffold. This is actually digits that we're engineering. These are being layered, one layer at a time. First the bone, we fill in the gaps with cartilage, we then start adding the muscle on top, and you start layering these solid structures. Again, fairly more complex organs. But by far, the most complex solid organs are actually the vascularized, highly vascularized, a lot of blood vessel supply, organs such as the heart, the liver, the kidneys. This is actually an example, several strategies to engineer solid organs. This is actually one of the strategies. We use a printer, and instead of using ink, you just saw an inkjet cartridge. We just use cells. And this is actually your typical desktop printer. It's actually printing this two-chamber heart, one layer at a time. You see the heart coming out there. It takes about 40 minutes to print, and about 4 to 6 hours later, you see the muscle cells contract. This technology was developed by Tao Zhu, who worked at our institute, and this is actually still, of course, experimental, not for use in patients. Another strategy that we have followed is actually to use decellularized organs. We actually take donor organs, and organs that are discarded, and we then can use very mild detergents to take all the cell elements out of these organs. So, for example, on the left panel, top panel, you see a liver. We actually take the donor liver, we use very mild detergents, and by using these mild detergents, we take all the cells out of the liver. 2 weeks later, we basically can lift this organ up. It feels like a liver. We can hold it like a liver. It looks like a liver, but it has no cells. All we are left with is the skeleton, if you will, of the liver, all made up of collagen, a material that's in our bodies that will not reject. We can use it from one patient to the next. We then take this vascular structure and we can prove that we retain the blood vessel supply. You can see actually that's a fluoroscopy. We're actually injecting contrast into the organ. So now you can see it start. We're injecting the contrast into the organ, into this decellularized liver, and you can see the vascular tree that remains intact. We then take the cells, the vascular cells, blood vessel cells, we perfuse the vascular tree with the patient's own cells, we perfuse the outside of the liver with the patient's own liver cells, and we can then create functional livers, and that's actually what you're seeing. This is still experimental, but we are able to actually reproduce the functionality of the liver structure experimentally. For the kidney, as I talked to you about the first painting that you saw, the first slide I showed you, 90% of the patients on the transplant wait list are waiting for a kidney. 90%. So another strategy we're following is actually to create wafers that we stack together, like an accordion, if you will. So we stack these wafers together using the kidney cells, and then you can see the kidney, these miniature kidneys that we've engineered, they're actually making urine. Again, small structures. Our challenge is how to make them larger, and that's something we're working on right now at the Institute. One of the things that I wanted to summarize for you then is what is the strategy that we're going for in regenerative medicine. If at all possible, we really would like to use smart biomaterials that we can just take off the shelf and regenerate your organs. We are limited with distances right now, but our goal is actually to increase those distances over time. If we cannot use smart biomaterials, then we rather use your very own cells. Why? Because they will not reject. We can take cells from you, create the structure, put it right back into you, they will not reject. And if possible, we rather use the cells from your very specific organ. If you present with a deceased windpipe, we'd like to take cells from your windpipe. If you present with a deceased pancreas, we would like to take cells from that organ. Why? Because we'd rather take those cells which already know that those are the cell types you want. A windpipe cell already knows it's a windpipe cell. We don't need to tease it to become another cell type. So we prefer organ-specific cells, and today we can obtain cells from most every organ in your body except for several which we still need stem cells for, like heart, liver, nerve, and pancreas, and for those we still need stem cells. If we cannot use stem cells from your body, then we'd like to use donor stem cells, and we prefer cells that will not reject and will not form tumors. And we're working a lot with these stem cells that we published on 2 years ago, stem cells from the amniotic fluid and the placenta, which have those properties. So at this point, I do want to tell you that some of the major challenges we have. I just showed you this presentation. Everything looks so good. Everything works. As you know, these technologies really are not that easy. Some of the work you saw today was performed by over 700 researchers at our institute across a 20-year time span. So these are very tough technologies. Once you get the formula right, you can replicate it, but it takes a lot to get there. So I always like to show this cartoon. This is how to stop runaway stage. And there you see that stagecoach driver, and he goes on the top panel, he goes A, B, C, D, E, F. He finally stops the runaway stage, and those are usually the basic scientists. The bottom, those are usually the surgeons. I'm a surgeon, so that's not that funny. Okay? But actually, method A is the correct approach. And what I mean by that is that any time we've launched one of these technologies to the clinic, we've made absolutely sure that we do everything we can in the laboratory before we ever launch these technologies to patients. And when we launch these technologies to patients, we want to make sure that we ask ourselves a very tough question. Are you ready to place this in your own loved one, your own child, your own family member? And then we'll proceed. Because our main goal, of course, is first to do no harm. I'm going to show you now a very short clip. It's a 5-second clip of a patient who received one of the engineered organs. We started implanting some of these structures over 14 years ago. So we have patients now walking around with organs, engineered organs, for over 10 years as well. I'm going to show you a clip of one young lady. She had a spina bifida defect, a spinal cord abnormality. She did not have a normal bladder. It's a segment from CNN. We are just taking 5 seconds. This is a segment that Sanjay Gupta actually took care of.
I'm happy. I was always afraid that I was going to have like an accident or something. And now I can just go and go out with my friends, go do whatever I want.
See, at the end of the day, the promise of regenerative medicine is a single promise. And that is really very simple: to make our patients better. Thank you for your attention.